Today I'm going to talk about the input resistance of the following circuit. And we're going to try to derive this. We have an R. We have an R here. We have an input current. We have an input voltage, U. Yeah. We have another resistor here. We have another resistor here. And it goes on forever. So there's no end to it. Yeah. So this RR circuit will go on forever. And the question is, what is the input resistance if we look on this point, on this terminal? So the question is, what is R? Well, R equals U over I, according to Ohm's law. So we're going to use in this example Ohm's law, which is R equals U over I. And we're going to use Kirchhoff's law. And Kirchhoff's law tells us that if there's a current going into a node, then all the currents must come out of the node in the same size. In other words, I equals I1 plus I2. This always needs to hold on all nodes. Currents are conserved. Yeah? So we're going to try to calculate this circuit. Before we do that, we're going to do two small sub-calculations that we're going to use later on in this derivation. If you have a small circuit with a voltage U and a current I, and there are two resistors in series, yeah, when they are attached to each other it's called in series, we can calculate this according to Ohm's law. U I equals I times R plus R. So if in series, you can add up resistances. Yeah. Now let's take a look at what that means if we do two resistors in parallel. In parallel is the following. So we have, for instance, an R1 here and an R2 here. We need to calculate what the resistance will be on this terminal looking into the circuitry. And we can see that, again, according to Ohm's law, U equals I1 times R1, right? If you have an I1 here, it will be I1 R1. Same for here, if you have an I2 there, you can say U equals I2 R2. What is the resistance on this terminal? The resistance R equals U over I. And according to Kirchhoff, I is the same as I1 plus I2. So I1 plus I2. I1 according to this one, we can fill out. That's U over R1 plus U over R2. Yeah. So the total resistance here, we can simplify this a little bit, and if we do that, we will see that the total resistance is R1 R2 by multiplying top and bottom with R1 R2 and dividing by U. The U will go away. You will get this resistance. So if you have two parallel resistors, you can calculate it like this. The replacement resistor for that is this formula. And if you add them up, for clarity, we can make this R1 and R2. You can just, if they are in series, you can just add them up. Yeah, so now let's go back to this circuit, and I'm going to write it in a slightly different way. What we're going to calculate is this. Plus, minus U. We will have an R. And this is the resistance at N. looking inside, the total resistance of the whole circuit is Rn. We will have an R here again, right? There's an I here, as before. And now here you have essentially a resistance, only one resistance, and that's Rn minus 1. It's a little bit further down the line. This is a very long line with all these resistors in series, all these RR circuits attached to each other. And the resistance here is essentially Rn minus 1. Yeah, if you have n of these things, the resistance here is Rn, the resistance here is Rn minus 1. Yeah? So what's the total resistance of this circuit then? Well, we saw if it's in series you can add it up. So Rn, total resistance here is R, right? Plus the parallel resistance of those two. And we know that it is something like this. So that's R times Rn minus 1 divided by R plus Rn minus 1. Yeah? So the total resistance on Rn is essentially this. That's quite important. Now, if we look at this, and if n is really, really big, right? There are lots of these little circuits all the way up to infinity. Then Rn is essentially in its limit the same as Rn minus 1. So in the limit, n going to infinity, we can say that Rn, let's call this R total, or Rs, let's call this Rs, the total substitute of all the resistance in the circuit, is R plus R times, then this is also S, divided by R plus Rs. Right? So now we can simplify this a little bit. We can multiply left and right by R plus Rs, which we will do. And then we will get R plus Rs times Rs on the left hand side equals R plus Rs here plus Rs. Yeah? Now we can work this out a little bit more, and we say Rs plus Rs squared, right, that times that, equals R squared, R times R, plus R times Rs, that times that, plus R times Rs. Yeah? Now we can work this out even more. We can remove one of these on the left and on the right, and we can take everything to the right, and then we get something like Rs squared, we leave that, minus R dot Rs, right, that goes to the other side, minus R squared equals 0. So here we have a formula which we can actually solve. Now we can use the ABC formula to see what Rs will be. So we do the ABC formula and we will see Rs minus B, that's R, plus minus, but only the plus has real world value. The minus doesn't work out because you get a negative resistance, and negative resistances do not exist in the real world, at least not in this context. So we do R plus, and then we get B squared, which is R squared, minus 4 times A, which is 1, times C, which is minus R squared, divided by 2. And then we get R plus 5R squared, right, divided by 2, which is R we can take the r out because it's always positive, and we get 1 plus the square root of 5 divided by 2. And that will be the total replacement resistance of the whole network. And if you look carefully, one of my previous videos, this number also came up, the golden ratio, with the Fibonacci series. So that's pretty cool that you have a resistance of this whole circuit, if you would go on forever, that will have this value. Yeah, 1 plus square root of 5 divided by 2 times r, which is a fairly simple formula. Okay, I feel this is a good time to stop. If you like this video, please like and please subscribe, and I will see you in the next one.